Yesterday, we looked at price impact. I mistakenly called it slippage. Slippage is actually the change in price after execution. Price impact is the implied impact on prices based on the pool reserves. Thank you, Shin, for correcting me on that. Today, we're going to be going further and looking at what is the volatility of token liquidity reserves and swap rate, the actual swap rate, and how can you try and relate the two? This should give us a better intuition in terms of how stable a pool is. I'm going to let Jackie walk you through the logic and the query.
Thanks, Andrew. So, like Andrew mentioned, we want to compare the volatility of liquidity versus the swap rates because we want to investigate the relationship between paired liquidity and swap rates. For example, if the price of wrapped ETH with respect to USDC changes, would we observe, on the other hand, the LPs making moves, adding or withdrawing liquidity to the pool? So with that in mind, let's talk about the logic. So to compare the two variables volatility, the liquidity versus the swap rate, we first need to compute the variables. So let's just write that down. So we are comparing the volatility of liquidity versus swap price. So we need to first get the liquidity. To get the liquidity, we need to use the pair event sync table, which we covered in day 9, to get the latest reserve balances for each token for each day, because we're trying to do everything in a daily term. And then once we get reserve 0 and reserve 1, we are going to put them in a constant product function. So from here, we are going to get the reserve 0, reserve 1 per day. Once we get that, we're going to apply x times y equals to k formula, which is the constant product equation that defines how the pool is going to behave. So here we have the x, which is reserve 0, and then y, which is reserve 1. So the way we're gonna get k is going to be reserve 0 times reserve 1. And that will be our metric to measure both tokens' liquidity as it was designed for each day. Now on the other side, for the swap price, what do we need to do? We need to look at the pair event swap table that we've looked at a lot last week to get the actual swap rate. For example, this is how much wrapped ETH was worth per USDC. Because we're trying to look at it on a daily window, we are also going to take median instead of average to remove the outliers. We only need to get one side of the swap rate, so we can choose to get, let's say, token 1 over token 0's rate instead of both, because both are just a measurement of the same thing, just reversed. So we can just take token 1 over token 0 as the swap rate to measure the second variable. Once we get the K and the swap price, we need to take the percent difference. Why is that? Because we want to be able to compare these two metrics, but they're on this different scale. So just think like when you want to compare your weight versus your height, they're measured in very, very different things. So you have to adjust them to be on the same scale before you can make sense of the comparison. So that's what we're going to do. We're gonna take the percent difference between today versus previous day for both of these variables. Once we get that, we're gonna take the standard deviation for the percent difference to measure the spread or the volatility of each of the variable. Once we get that, then we are able to compare these two standard deviations. So we can then compare how much more volatile is liquidity versus the swap price. So then we can just do a simple division, right? We can do like a standard dev of the percent diff of liquidity over the standard deviation of the percent difference in the swap price. then we'll be able to see the magnitude difference. Then we'll be able to get a sense of the original question. How much more volatile is the liquidity versus the swap price, which will feed into the stability question that we've been investigating. All right, with that being said, let's get into the query. We know the drill. Let's do select from, find our Uniswap v2 project, find the pair, find the events, find the sync events, aliasing that as us. At this point, we know in order to make sense of like what is the token address that exists in this pair and find the correct decimal to adjust different tokens, we need to join on the pair created event table as well as the tokens.erc20 table. So we're just going to do that right now. So left join on pair event created. We are going to join that on pc.pair is equal to s.contract address. And then we are going to join by the tokens, tokens.erc20, token 0 on tk0.contract address is equal to PC's token 0, right? And then also making sure that the blockchain is Ethereum blockchain. And then going to paste this for token 1. Now we are ready to select. So we need to do dates trunk because we are interested in the daily data. We want the block time as our time. Then we can grab the information for this pair. We have the pair's address. Then we are going to grab token 0's address and token 0 symbol, and then the same thing for 1. So pc.token 0 as token 0 address, token 0 dot symbol as token 0 symbol. Do the same thing for 1. Moving on, we need to grab the reserve. That's what we came here for. So we know we need to cast it because it's a varchar. Then we need to adjust. And we need to coalesce because in case we cannot find the correct adjustment. Token 0.decimals. And then we're going to just default that to 18 decimals as our reserve 0. Going to do the same thing for 1. For 1. Okay. So one more thing we need to do is to take the latest reserve balance for each token because we only need one record for each day and we want to take the latest for the most accurate. So we need to find the latest row for that day. We need to apply a Windows function. So row number over partition by each of the pair, then also partition by the date. Order this by the time within the day because we want to find the latest. So we want to do descending, and then this we're gonna name as our last sync. We're gonna put this in a subquery. So select star from we're gonna A where last sync is equal to 1. Let's just start our investigation by looking at the USDC wrapped ETH pair, and later on we can plug in the pair address for a few different pairs to see how different it would be. So contract address is equal to, so per usual we're gonna do USDC wrapped ETH as our default. Okay, let's also just limit the investigation in the past 20 months to begin with. Then let's take a quick look to see what this looks like. Let's just see the past month, what happens. There might be a lot of data for the past month, so let's just do limit to 10. All right, let's take a quick look. This looks all right to me. Let's move on. Let's start our CT now with reserves as. So this is our reserve information. Now let's move on to the raw info for the swaps. We already got what we want for reserves. We can later on adjust the reserves to get the K for liquidity. In terms of swaps, let's do something separate. Select start from. So we want the pair event swap table. So we're also going to alias this as us. And then we know the drill at this point. We need to left join on these tables to get the necessary information. So we are doing the same drill. We're doing each day. So we're truncating the time to day. Then we are taking the contract address as the pair. And then we are going to adjust the amount to 0 in and out and amount 1 in and out correctly. So we are first going to cast this as a double and then going to divide it by the correct decimal if possible. So and then that's gonna be amount 0. And then we are going to repeat that 3 more times. Let's get amount zeros all together. And then let's get amount 1. Let's change this to be token 1, and amount 1 out, amount 1 out. So we've got the roll swaps adjusted for the correct decimal. Let's just limit it to the correct pair. So we want a particular pair, and we are also looking for the past month. We can test this by doing a limit to 10. Okay, looks all right. We are going to call this swaps decimals because we adjusted for the correct decimals with that inside of here. Now we need to find the swap rate, right? The actual swap price. So we need to identify, is it like a 0 to 1 swap or a 1 to 0 swap? So we're going to we're just gonna call this daily swap rates. And then, so we are going to select from swap decimals, right? What are we getting? Obviously, we still need the time. We still want the pair. And then case. Based on the results here, we can construct our case statement. So when the amount 0 in is not 0 and amount 1 out is not 0, then we'll take the amount to 0 in divided by amount 1 out. It will be a null, and then we are naming this as swapping 0 to 1. We can see this happening here. Okay, another case that could happen is swapping 1 for 0, right? Swapping 1 for 0, which would be here. So amount 0 out and amount 1 in should not be amount 1 in should not be 0. So amount 1 in divided by amount 0 out. So that's our swap rate, or the price of 0 to 1 and 1 to 0 token. Okay, and once we get that, we need to take the median. So we're doing select from daily rate. As usual, we're gonna do the time and then pair, and then we are taking the median. So we are going to apply approximate percentile function 0.4 0.5. 50th percentile is the median as swap 0, 1. And then going to do the same for 1, 0. Lastly, we're going to be grouping by our pair. Honestly, we didn't really need this pair, but that's okay. Let's take a look at this. So let's get rid of the limit here. Let's do a limit here. Why doesn't it like that? Oh, forgot an S. Mismatch select. Ah, another S. Looks like we have our sanity check result around this time 1200. This looks pretty good to me. Now we're ready to combine both of them. Okay, so this is our reserve block, right? So this is our swap rates block. And then we are going to take all of this, deleting the limit part. Okay, so we have the swap rates part and the reserves part, and now we are able to combine them to get our liquidity K and take the swap price token 1 over token 0. Okay, so let's do that. Reserves, swaps, combined as. Okay, so we are doing select from reserves as R, and then we are doing a full outer join, right? Because we want information from both sides. So swap rates us on what? On r dot time is s dot time, and the r dot pair is equal to s dot pair. So what do we need? Coalesce on our time, because we're trying to take info from both sides as time, and then again coalesce the pair to get the pair. Typo here. And we want to get token 0 and token 1. So here we are going to coalesce to get the, if we can get the symbol, then we get the symbol. But if we cannot get the symbol, then we get the address as token 0. And then apply the same thing for 1. Oops. Token 1. Then now we are ready to get the reserve 0, right? Reserve 1, and then swap. We don't need swap 0, 1 because we just need to take one of the two. Swap price, we're taking 1, 0. We now need to generate full sequence for every day in case there are some gaps missing, because we are looking at 2 time series for both of these 2 separate variables that we're going to investigate, and then we want to make sure we're not missing any of the days just in case. So we need to generate a time series sequence for each day. How we're going to do that, we're going to first generate a time sequence. So with time seek as, okay, so we are going to use the sequence function as before. So we need the start and then end and then the intervals, right? So start would be the first day from this reserve swaps combine. So first day, so we need to get select and then the minimum of the time as time from this CTE. Then we need to cast the minimum back as the timestamp. The end would be today, so date trunk day is basically now, so we're casting now as a timestamp, and then we're date truncating now today's date. And then what is our interval? It's gonna be interval 1 day. We want to increment this every day. Okay, so we're gonna call this time column. With that in mind, we are going to needing to do a cross join and an unnest, because sequence produce a horizontal array of all the dates, and then we need to switch this into like day 1, day 2, day 3, day 4. So we want to unnest it, and then we need to do a cross join. You can read up more on why we are doing this in this Stack Overflow, which I will link here. Okay, so let's cross join and then read more for why we need to cross join on nest. Okay, so we are going to select from time sequence, and then we're first going to cross join on the unnest of the time, right? Unnest of the time column here. And then when we do that, we are naming this a table time and then the column as time. Okay, and then we're choosing this table time dot time, right? Okay, so that, let's take a look at how it goes. So select star from time series, and let's take a quick look. Okay, looks like it's as expected. We're good to go. So now let's combine this time series with our swaps combined. The idea here is maybe some days, like day 1, we have information, right? Day 2, there's no information, but we have the time series date generated for that day. So what we need to do is we need to take the info from day 1, and then we need to forward fill this to day 2. Hopefully it makes sense once we write it out more. So here we are joining with time series and forward filling reserve swap rate for the null days, right? And then before that can happen, because we also want to make sure we have the token pair information, and then here you can see it's like just one column of time, so we need to also have the token 0 and token 1 information, and we need to do a join of them together so that we get, you know, day token 0 token 1 for the information, just so we have it later. So here we're just gonna quickly grab the pair info as, so select. We only want distinct. Basically we should only have one row here because we're looking at one pair. From reserve swaps combined. Okay, so once we get that, we can do this here. Reserve swaps field. Okay, as, what are we doing here? So select from, we are going to do the cross join like I was describing. So select time, right? We want time from this time series, and then we want all the information from the pair, right? We want to cross join them from time series pair, and then we have to give the subquery a name t, and then here we're just doing a cross join to get a row with token 0 and token 1 info for each day. Once we get that, we need to do a left join because this cross-joined table would have all the rows that we need, so we can anchor our join on top of that. So left join on reserve swaps combined, right? So we're going to call this C, and then on t dot time equals to c dot time. Okay, now we are ready to grab our info. So we can do t dot time. That will be our date, right? T dot pair, that's the pair address. T dot token 0, T dot token 1, T dot token 1. So we need to have both reserve 0 and 1 for our equation x times y equals to k later. So we're gonna start forward filling both of them. So coalesce first, we can see if the 0 is null or not. If that is null, then we are going to take a lag. So the lag function takes however many rows you define that comes before the current row, right? So if we just straight up do a leg 0, then by default, the offset is 1. So that means we're taking 1 row above the current row. And then we're doing like an over, right? So how are we ordering this Windows function? We are ordering by the time or the date, right? But possibly the previous row could be null as well, so we can apply ignore nulls. So that tells us that we're gonna grab the first non-null row that comes before this current row of reserve. So that would be our reserve 0. And then the same thing we are going to apply to reserve 1. Okay, so that is all we need for the reserve side of things. And then for the swap price side of things, we have our swap 1.0. We have our swap 1.0. So we are going to forward fail the same way to get to the swap 1.0. Let's just take a quick look to see. Select star from reserve swap field. Okay, looks like we have some results. Sanity check passes. We're good to go. So exciting part, we're gonna get the 2 metrics that we had been talking about, the K metric and then the token 1 over token 0 swap price. So we are going to do this liquidity price, and then in the notional, select from reserves swap field. We need the time here, we need the pair token 1, and then reserve 0 times reserve 1, which would be our K in the constant product equation. And then we're gonna take the 1.0 as price. And now we are ready to find the percent diffs between current day and previous day. As we said, we need to compare the 2 in the same scale when we eventually compare the standard deviation with the volatility, the spread of things, right? So reserve swaps diff. We can call this diff like that, actually. Diff as, okay, so select from this table, right? And then we are going to do n, and then we're gonna do n dot everything. We want everything here. And then we are introducing our new percent difference. So today, okay, liquidity current row minus the last row, right? Again, we're using the log function to grab the last row, and then by default, it's gonna grab the first row previous to this. If you want more offset, you will just specify this, like 2, 3, whatever you need. Over partition by pair, order by time, okay? So that is our current minus previous, and then this is divided by the previous. And then we're gonna call this K liquidity diff per percent, okay? And then coming back here, we are going to copy this entire thing, but apply it for the price. So price, partition over pair, order by time, price, and then we're gonna do price diff percent. Select star from liquidity price diff. And this time, honestly, let's just see what happens in 20 months. All right, we have the results for USDC wrapped ETH pair. So let's create a visualization to look. We want to see the liquidity. We also want to see the price and enable right access. Right, so, let's see. Interesting. So let's visualize the percent difference to see if we can observe anything. Percent diffs of K versus price. Let's put this as notional K versus price. Okay, so we are doing the K and price percent diff, or diff percent. Enable right x. Oops, did not mean to do pi right. And then, yeah. Let's see. Wow. Okay, so it moves a lot, and then in particular on this 20 months, yeah. So looks like on this day, November 11th, the liquidity changed a lot. So we can see these spikes in terms of the changes, but if we just look at the percent difference for K and for price like this visually, it's really hard to extract how volatile are the K in relationship to price, right? We want to have a metric to help us quantify this variations, this volatility. And that would be when we do the standard deviation. Okay, so let's comment this out, just make a note to ourselves. This is for data exploration before taking standard deviation. Okay, so we do select star from this price diff D. Okay, and we want the pair to be here, and then let's make it nicer, right? We can concat token 0 together with token 1 to make it nicer as pair symbol. Okay, so standard deviation side, we are going to apply the standard std dev function. Okay, and then we're taking the standard deviation of the percent differences in the K for the liquidity as the K standard deviation. So same thing, we're going to do that for the price percent difference, and then we are going to call this the price standard deviation. Then we want to see if one's volatility is a lot bigger than the other one, right? We want to see when the price moves a lot, does the K moves a lot more than the price. Okay, so the way we can do that is we do a division very simply. So we divide the standard deviation by the standard deviation, and then we're going to name that as magnitude. And then lastly, we are going to group by 1 and 2. So group by each of the pair. All right, we have the result for USDC wrapped ETH. So let's just record this. Because then we can take a look at a few different pairs to see how they're different. Okay, so this is for USDC wrapped ETH pair, and our K standard deviation is equal to, let's make a prettier table than this so we can read it better. Okay, we are going to format the standard deviation in 0.0%. Let's do that. Let's do that as well. And then let's do the magnitude in 2 decimals. Okay, beautiful. In case it's more, we're gonna preemptively do that. That is 10.64%. And then the price standard deviation is equal to 4.3%, and then the magnitude is equal to 2.47. Okay, so what does this tell us? This tells us the volatility of the K, the liquidity, is not much more than the volatility of the price, the swap price, right? So that means that when the prices change, like when a token price change in this USDC wrapped ETH pool, the liquidity is fairly stable. Like it doesn't change in an out of proportion way as compared to the price, right? Because the magnitude is only 2.47. So the volatility, the standard deviation of the K is only 2.7 multiples than the price standard deviation. Maybe this doesn't make sense quite yet, so let's look at another pair. Another pair that I would expect to be a little bit more volatile in terms of the liquidity is SHIB. So let's go with that. So here, this is a Core fork from day one, right? We were trying to get what pairs contains USDC. So here, this Core just try to get the pair that contains USDC. And so if I search for SHIB, I get the pair address of SHIB USDC. So let's come back here and let's update this to be SHIB USDC and let's run it. Okay, so SHIB is, wow, okay, so this is like a lot. So how can we address this? Can we address this in an A? Yep, we can do that. And then we can also put this in an A. Okay, so the standard deviation is so much so it's super volatile, the K. And then the price is also super volatile, but comparatively, right? This is in the billions. This is in the K. So the magnitude is in the millions. So what does this mean? This means that when the price of like SHIB USDC changes, the liquidity changes a lot more than the price change, right? So this pool is not that stable as compared to a pool like USDC and wrapped ETH. Because you can see the magnitude is 1.49 million, okay? Something else to keep in mind is just like the time window. We're only looking at the past 20 months. Normally when a pool is first created, in the beginning days, it's a bit wobbly. So here we're not necessarily comparing because the time that each of the pools started are different for each one of them, right? So that is like another factor that we are not taking into consideration here. Anyways, that is the answer for day 11.
Thank you, Jackie. It's really interesting to see how the volatility of different tokens. If you want to take this further, try and find a better method for comparing the volatility of the liquidity constant versus the swap prices in a better way than just magnitude. Tomorrow, we're going to finish off all 12 days by clustering everything we've learned from the stability portion to compare all USDC pairs and see which ones have the highest liquidity stability or not. So, see you tomorrow for the last one.